Here we're looking at the mesh current analysis of this circuit. If we were trying to find, say, a voltage here or a current here, how do we go about it? This is too complicated to solve with series and parallel resistor analysis, so we're going to try and solve this with a thing called mesh current analysis. Now, the thing about mesh current analysis is it uses Kirchhoff's voltage law. We calculate voltages around loops and do some magic, and we can solve this circuit. So the first thing we do is, because we're using Kirchhoff's voltage law, we use the voltage around a loop, we define some loops. Now we've drawn them all clockwise in this case. We can actually draw them in different directions, but that makes your solutions more complicated. So if you draw them all the same way, so all these loops are drawn in a clockwise direction, and these loops represent the current flow around this loop. Every element in the circuit is in a loop. There's nothing missed out. We've not crossed any loops over because that makes things a bit more complicated. Now if we looked at a loop 2 here, if we draw the current as it flows through those resistors, I've put a positive symbol on each resistor where the positive end of that resistor would be relative to the current of loop 2. And if we draw the voltage vectors with the arrow at the positive end, you'll see that we can add all three voltages around that loop, and under Kirchhoff's voltage law the sum of those three voltages will equal 0. If we did the same for loop 3, notice that resistor 5, the positive sign flipped ends, because we're now considering resistor 5 relative to the loop 3 current. And if we put the voltage vectors on, they all flow in the same direction, so we can add them. If the voltage source was the other way up, so the positive was at the bottom, then we would subtract the voltage source. So we'd have the voltage across R3 plus the voltage across R5 minus the voltage source equals 0. So we've worked out which end relative to the loop current is positive for those components, so we can tell whether we're adding or subtracting the voltage source. And we can do the same for loop 1. Now, for resistor 1, it's quite simple. It's current 1 times resistor 1 is voltage. And for resistor 4, it's the same thing. Current 2 times resistor 4 gives us the voltage across resistor 4. But if we were looking at resistor 2, we've got the current of loop 1 flowing in one direction and the current of loop 2 flowing in the other direction. So when we come to do the calculation, here's the voltage across resistor 1. Here's the voltage across the resistor 2 when we're considering loop 1. We put the loop 1 current first, subtract the loop 2 current, multiply by the resistor. That gives us the voltage across R2. Then if we're looking at this one, we've got loop 1 and loop 3 currents. Loop 1 current minus loop 3 current times the resistor equals 0. So loop 1, we consider I1 first in each component, as it's got the little blue underline. If we're looking at loop 2, we'd consider the I2 current first in each component there, and the same for loop 3. Now, leaving that circuit, how do we deal with current sources? So imagine we've got a current source in that position. We don't know the voltage across the current source, so we can't work out the loop voltages, but we do know that I1, loop 1 current, is equal to the current source current, because the arrows are in the same direction. So we don't need to work out those voltages around that loop. We just say I1 equals IS, and then when we work out the voltages around loop 2 and loop 3, instead of using I1, we put in IS, and we only have two unknowns in two equations. If we turn that current in the other direction, current source current is opposite to the loop current, so it's I1 equals minus IS. What about if we put the current source there? We can't work out the voltages around loop 1 or loop 2. So what we do is we bypass that current source, we combine loop 1 and loop 2 like this, we work out the voltages along the blue line. So we skip over the current source. Now if you look at the bottom of this slide, you can see that I1 minus I2 equals IS. So we can actually, once we know that I1 minus I2 equals IS, we can rearrange that equation and then substitute into both the other two equations, and we'll remove one of our unknowns. So either we can remove I1 from both equations, or we can remove I2 from both equations, depending on our choice. Okay, so now let's go back to our original circuit and we'll substitute in some real values and see if we can't solve this. These are the same values as in the node voltage example. So we'll put these into the equations and we'll simplify those three equations. We've expanded out the terms where there was multiple currents in the brackets, and then we've brought all our I1 terms together and our I2 terms together and our I3 terms together in each of those loop equations. So now we can take those three equations and we can use them in our simultaneous equations. And in this case, we've decided to try and get rid of I1. So by multiplying this equation by 3 and then adding it to this equation, the I1 term will have 45 and 45, so the I1 term will disappear. So we're just left by multiplying this whole equation by 3 and adding it to this equation. We end up with this equation here. To get a second equation, multiplied this equation by 2, multiplied this equation by 9. That gave us 90 times I1 and minus 90 times I1, so that when we added the resultants, we ended up with no I1 term. So now we've got two equations in two unknowns, just I2 and I3, I2 and I3. So now we're simplifying, we're rearranging this top one so that when we add the two together, we can remove the I2 term. So I'm multiplying this equation by 75 over 60, so we'll end up with 75 I2, and when we add it to this equation, I2 will disappear. So we add the two, and we end up with this. I3 by 83.75 is minus 180, gives us this current. We can now substitute that current into either of those equations. I've substituted it into the first equation, and that's allowed us to come up with I2. Now we take I2 and I3 and substitute it into another equation, one of our original equations, and that allows us to calculate I1. So now we've got I1, I2 and I3. Let's try and calculate some voltages. So for instance, if we want to calculate the voltage at this point here, now it turns out I2 does not flow in the direction of the arrow, actually flows in the opposite direction. So the current flows into the top of the 5, so this will be the positive end, and it's 4.4775, 4.48 volts here. This is actually the value that we calculated with node voltage analysis. So this voltage here is the voltage we calculated with node voltage analysis. Let's try and work this one out. Now in this case, again, I3 does not flow in the direction of the arrow. The answer was negative, so I3 flows this way, and I2 flows this way. I2 is flowing up, I3 is flowing down, I3 is bigger, so the resultant current, this plus this, the current will be flowing in the top, so the top will be positive. And it works out 6.27 volts. That's the voltage calculated with node voltage analysis. So the voltages that we calculated using mesh current analysis are the same voltages as we calculated with node voltage analysis. So these two methods give us the same solutions.